Earlier on, we talked about a situation where we had a single individual. And that single individual had an IQ of 130. And so we knew IQ was normally distributed with mean 100 and standard deviation of 15. And so with that information, we could determine the proportion of the population or the other way you could look at it is, if you were to select a person at random, what's the probability? Either way, proportion or probability of individuals that would have an IQ less than or equal to 130. And we did a bunch of math, and we determined that about 98% of the population would have an IQ of less than 130. So that was the earlier example. So now what we're going to do is move on to drawing inferences about population means. And so what we're going to do is we're going to assume that our underlying population, the random variable y, is normally distributed with mean equal to 20 and standard deviation equal to 3. And then we're going to collect a sample. And what we're going to discover is that in our sample, that y bar is going to turn out to be 22.5 in the sample that we collect with a sample size equal to 10. And so what I now want to think about is, what is the probability of getting a single sample, single observed sample y bar with a value equal to 22.5 or more if the underlying assumption that the random variable y was normally distributed with mean 20 and standard deviation was true. And that really forms the basis of a very important idea in statistics, the idea of null hypothesis statistical testing, which is sometimes represented as NHST. Null hypothesis statistical testing. So the way this is going to work is we're going to start off with our assumption that y is normally distributed with mean equal to 20 and standard deviation equal to 3. And then we're going to go through some absolutely correct, perfect logic. And what we're going to do is calculate the probability of getting a mean y bar equal to 22.5 or more based on a sample size of 10. And this probability we refer to in statistics oftentimes as a p-value. And we're going to examine our p-value. And if it's very low, what are we going to do? What are we going to do if we get a probability of getting a sample mean of 22.5 or more? We decide that's a very low probability. Well, if our logic was correct, and we're going to assume that, we know that's correct, it's mathematically certain, then there must be an error in the assumptions. And we'll go over this later, but typically what we assume is that the error is in the mean. And so the reason that this is called null hypothesis statistical testing is we've posited at the beginning that the population mean was equal to 20. We go through this process, and that's going to provide a formal statistical test of the hypothesis that the population mean is actually equal to 20. So, let's do some calculations. So, we assumed that our sample mean was equal to 22.5 based on a sample size n is equal to 10. And as always in these situations, what do? We're going to calculate our observed value of z, which is equal to y bar minus mu over sigma divided by root n. Now, where the heck did this come from? Let's recall where this came from. Well, y bar is pretty obvious. That's going to be 22.5. How about this other stuff? Well, remember that we assumed that y, our underlying population, was normally distributed with mean mu and standard deviation sigma. Well, we showed in our last videos that if that was true, then y bar is going to be normally distributed with mean mu and standard deviation sigma over root n. And let's think again about what this means. Y bar. What's y bar? Y bar is a random variable. It's the set of all possible lowercase y bar, the set of all possible sample means. And what we know is, if we consider the set of all possible sample means and their distribution, the mean is going to be the same as the underlying population. But if we consider all possible sample means, when we're thinking about sample means, the variability is going to tend to be reduced because, the bigger and the smaller are going to tend to average out. So this is a random variable. If this is a random variable, then we can think of this thing as being a probability density function. But it's the probability density function of a sample statistic, and therefore we give this probability density function a special term. We refer to it as a sampling distribution. And there's one other important term, and that is when we think about the standard deviation of this special thing, the special PDF, the sampling distribution, it has a particular name that's known as the standard error. Sometimes referred to as the standard error of the mean. So, there's our y bar. All this explanation here provides an idea for the formula. We assumed sigma was equal to 3. We know that n is equal to 10, and the null hypothesis that we're interested in is equal to 20. So now it's just a question of doing some algebra. So we pump those numbers in, and we get z, do this in black. Z equals y bar minus mu over sigma divided by the square root of n, which is going to be equal to 22.5, the observed mean, minus the null hypothesis, which is 20, divided by the standard error, the standard deviation of the set of all possible sample means, and that's going to be equal to the standard deviation of the original population, which was 3, divided by the square root of our sample size is 10, and that turns out to be a value of 2.63. So the whole idea about calculating a z value. Why do we calculate a z value? Well, what we know is that if we consider all possible values of this, all possible values could be represented as a random variable, and we're just going to substitute capital Y bar for the lowercase y bar and get y bar minus mu over sigma root n. And what do we know about that? What would we know about all possible values of this? They would be normally distributed with mean 0, standard deviation 1. That's our standard normal. And the whole idea of using the standard normal is that enables us to use the Z table, and that's what we're going to do now. So this is the standard normal distribution. And what we have in the margins here are the first two significant digits, and then in the margin here, the third significant digit of the Z value. And we got 2.63. So we got 2.63. 0.9957. So we got 0.9957. So what does that mean? That means is that if our Z value is actually 2.63, and I'll draw it in here. There's a value of 2.63, and we consider all this area here, that corresponds to 0.9957. And this little bit out at the end, this tiny bit at the end, corresponds to 1 minus 0.9957, which is equal to 0.0043. So this little bit out here is 0.0043. And what does that represent? That represents the probability of getting a Z-score of 2.63 or more. And the or more part is important. What's the probability of getting a Z-score of exactly 2.63? Well, again, we're dealing with a continuous random variable, so the probability of getting exactly 2.63000000 would be 0. So what we're getting is the probability of getting, this probability is 0.043, corresponding to the probability of getting a Z value of 2.63 or more. Okay, so let's go back to the whiteboard. So let's think again about how NHST, null hypothesis statistical testing, works. We start off with the assumption that Y is normally distributed with mean 20 and standard deviation 3. And then we go through some perfect logic. And with our perfect logic, we discover that the probability of getting the Y bar that we actually observed, which was 22.5, based on n equals 10, getting a probability of getting a Y bar this large or more would be minusculely small. You have a p-value of equal to 0.0043. So, that's pretty low probability. So what's going on? What's going on is we assume that there's an error here. And what typically we do in null hypothesis statistical testing is assume that we made a mistake in the mean. So before concluding, just a couple more points I want to make. The first one is that the example that we just went over is, again, somewhat artificial, somewhat oversimplified. It's really meant to set the stage for the next bits of the chapter that are meant to be more realistic. Some of the things that may strike you as a bit odd is, remember early, at the end, I think of the last video, I did this. I said, okay, Z was equal to mu minus, Y bar minus mu over sigma over root n, and that this was going to be 22.5. We know that. We're dealing with a scenario now where we're going to assume that the sigma is known. We're going to assume that that's equal to 3. Obviously, we know the sample size, and that's 10. But then in that last video, I did this. Where did that mu come from? Well, we can see now that where mu comes from, that is our null hypothesis. But what would induce us to have a null hypothesis of 20 as we had in this case? And that's a bit of artificiality, and that'll get cleared up in the next section. The other thing that we're going to clear up in the next section is this. The fact that we're assuming that the standard deviation is equal to 3. So this whole process ought to have struck you as being really weird. Like, if we're going through this process and trying to test the null hypothesis that the population mean is equal to 20, well, clearly we don't know what the population mean is. So can we imagine a situation in which we wouldn't know the population mean, but would know the population variance? I doubt it, not in the real world. So in the next section, we're going to start to get into something more realistic, where we're no longer going to assume that we know what the population standard deviation is. Rather, we're going to estimate it by using the standard deviation of the sample. So we'll stop there.